Okay, so welcome back. What we're talking about today, or what we're accomplishing today, is we're going to finish up Chapter 6 on gravity. And the next topic that we're going to get into to wrap up Chapter 6 is Keplers Laws of planetary motion. So let's get into this. We'll need to take kind of a historical picture here to understand what's going on with Keplers Laws. So Johannes Kepler, who these laws were discovered by and are named after, lived in the late 1500s, early 1600s, and he worked for this guy, Tycho Brahe, who was older than Kepler by like 25 years, and Brahe was a rich nobleman, so he was just basically royalty, and he liked to do astronomy for fun. He had a big observatory where he would observe the night sky, track the motion of the planets, and that was really his hobby. And Kepler, someone far less wealthy than Brahe, was working for him, okay, for a number of years in his life. And it turns out they didn't get along too well. I think the story is that Brahe was kind of a jerk, and Kepler didn't get along with him. So, you know, they didn't really see eye to eye, but at some point, Brahe passed away. He died in 1601, and Kepler, at that point, got to inherit all of Tycho's data. So all of this data he's been collecting for many, many years on the way the planets move in the night sky. Kepler got access to all of that. And in some ways, it was probably the best data you could get your hands on at the time. And what Kepler was interested in was looking for some kind of pattern in the data. Okay? Is there something I can find in this data that tells me something fundamental about the way planets in our solar system move? And he did find those patterns he was looking for. In fact, he discovered 3 mathematical laws, which I'm going to tell you about right now, which describe the way that every single planet in our solar system moves. Okay? Now Kepler, just to be clear, he came before Newton. He was before Isaac Newton, so he didn't have any idea of what gravity was or how it worked, but he was able to find these 3 laws of planetary motion, which really helped Isaac Newton later on figure out how gravity works. Okay? So let's go into the 3 laws of planetary motion that were discovered by Kepler. And the first one, Kepler's first law, says this: the orbit of each planet has the shape of an ellipse, with the sun at one of the focal points. Now, this is a big deal because back in Kepler's time, it was really commonly believed that every orbit was a perfect circle. People really had it in their heads that planetary orbits had to be perfect circles. It just had to be that way. And people were just really convinced of that. But Kepler showed that's not the case. Orbits are actually elliptical. Now, an ellipse, that shape, is just really a squished circle where you imagine taking a perfect circle and then squishing it along one end. So now you have a small side and a wider side, like this. Okay, so the focal point is something that was referenced here. We just said that the sun is at one of the focal points of the ellipse. So think back to what you know about geometry. What is the focal point of an ellipse? Well, for all points on this ellipse, this shape right here, the sum of the distances to the 2 focal points is constant. Okay? So let's take this point on the ellipse right here. The distance to focal point F1 is this line. The distance to focal point F2 is this line. For an ellipse, if you add those 2 distances together, it's always the same. It's a constant for the ellipse. So in other words, let's say I'm down here. The distance to focal point F1 plus the distance to focal point F2, it's the same value. It's constant for the ellipse. There's one other thing on this diagram about ellipses that I want to point out, which is something called the semi-major axis. So if we take the longest dimension of the ellipse, which would be from here to here, and then we take half of that, that's called the semi-major axis. Okay, so half the length of the widest side of the ellipse is the semi-major axis, and we're going to use the variable s for that. Semi-major axis s on the diagram. So actually, I want to show you a demo which basically gets at how do we draw an ellipse. Okay, so what I have here is a rubber band, and I've pinned a piece of paper down to a piece of corkboard at 2 different points, and basically think of these points as the focal points F1 and F2 of the ellipse, because I can draw the ellipse like this. As long as I keep this rubber band relatively tight, but I don't stretch it out, this distance plus this distance, the distance to the 2 focal points added together, is going to stay the same. Because of that, if I just sort of move my pencil around, I'm going to draw an ellipse as I go across the paper. Oops. Okay. Now that didn't go quite as well as I'd hoped. This corkboard is actually super grainy. But you get the idea that, okay, if this is a focal point and this is a focal point, the sum of these 2 distances, F1 and F2, is going to stay the same. That's really what defines an ellipse. Okay? All right, so that's Kepler's first law. It's basically the statement that orbits have the shape of an ellipse. Here's Kepler's second law. Here's what it says. A line drawn from the planet to the sun sweeps out equal areas in equal times. Okay, so what we're imagining is a planet moving in this elliptical orbit, like so, and we're going to draw a line from the sun to the planet and just see what kind of area that line sweeps out. So for instance, over here, let's say the planet is moving from position 3 to position 4. So again, if we take a line connecting that planet to the sun, it's going to sweep out an area which is shown right here. That's the gray shaded region. That's the area we sweep out. Okay, on the other hand, if we're over here, and I go from point 1 to point 2, well then this shaded region is the area that we sweep out going from point 1 to point 2. Okay, so what's being stated here is, if it takes the same amount of time to go from here to here, as it does to go from here to here, then we automatically know that these areas are equal. So we sweep out equal areas in equal times. That's basically what Kepler's second law is about. And there's a really important thing that this implies, okay? This implies that if a planet gets closer to the sun, it's going to speed up, okay? Because if you think about it, it's really close to the sun. If it's going to sweep out a bigger area, it has to move a bigger distance along the curve to actually sweep out that area. If we're over here, really far away from the sun, it doesn't have to move that great of a distance to sweep out the same area. What does that mean? We're moving faster over here compared to over here. So when we're getting closer to the sun, we're moving faster. When we're getting further away from the sun, we're moving slower. Okay, so actually, planets, if they're moving in elliptical orbits, are speeding up and slowing down depending on how far from the sun they are. That's the idea. And it makes sense because, of course, you'd expect something to speed up the closer it gets to the sun. So that's the second law. We're really just going to leave it at that. Now on to Kepler's third law. What does this say? This says that the square of the orbital period of a planet is proportional to the cube of the semi-major axis of its orbit. Okay, so that's quite a lot to take in. There are 2 quantities that we're thinking about in this third law, which are the orbital period, that's t. Remember, that's how long it takes the planet to go around the sun one time. The other quantity is the semi-major axis. So again, we think of the planet as moving in an ellipse, and half of that long side of the ellipse is the semi-major axis. So that's what Kepler discovered, is a relationship between period and semi-major axis. He found that the period squared is proportional to the semi-major axis cubed. That's what he found. Okay, so if the period squared is proportional to the semi-major axis cubed, we can write that as the period squared is some kind of constant times the semi-major axis cubed. That's the idea, right? Because when two things are proportional, then they're just related by a constant. That's what that means. So now we can rearrange this to say, if we divide out s cubed, t squared over s cubed is some kind of constant. And that's really useful to say. So, because it doesn't matter which planet in the solar system we look at, right? If we take the ratio t squared over s cubed, it's going to be the same. That number is going to be the same for Mars. That number is going to be the same for the Earth. It's going to be the same for Venus. Any planet in the solar system, that number is a constant. And so what we typically do when we apply this is we can compare two different planets in the solar system. So we'll give one of the planets the label 1, and we'll give the other planet the label 2. Because if this is a constant, then I can set that number equal for any two planets I choose. So I have t1 squared over s1 cubed equals t2 squared over s2 cubed. That's really basically how we're going to use Kepler's third law most of the time. Okay? So, with that said, I'm actually going to do a derivation. I'm going to show you where Kepler's third law comes from, why it's true, and here's what that looks like. So what I'm going to do is a derivation of Kepler's third law. In this case, we're going to think about a circular orbit. Okay? We're going to start by thinking about circular orbits. So Newton's second law, what does it say? F equals ma, but we know we're talking about something moving in a circle, so we're going to look at the radial direction. Net force in the radial direction equals m times acceleration in the radial direction. Okay, so if we're talking about a planet orbiting the sun, the force here is gravity. That's what's keeping it moving in a circle around the sun. So we have big G, big M times little m, those are the two masses, divided by r squared, that's the force of gravity. And on the other side we have m times v squared over r. So I'm kind of glossing over a lot of the details, but we've seen this a number of times up till this point. Force of gravity equals mv squared over r for something moving in a circular orbit. So what can we get from this? Well, let's solve for, or let's first cancel out little m. The mass of the planet doesn't really come into play. And let's multiply through by r on both sides. And v squared is going to be g big M over r. That's what we have. So this is saying the orbital speed squared is given by g big M over r. Now the orbital speed is, again, how fast the planet is moving in its orbit around the sun. If it's a circular orbit, we can think of that as being 2 pi r divided by t. So the circumference, that's how far you travel in one orbit, divided by t, that's how long it takes to do that. So I'm going to plug this in right here, where we have v squared, 2 pi r over t squared, equals gm divided by r. Okay, just plugging it into this equation. And, okay, so then we have 4 pi squared r squared, because I'm going to actually distribute everything in here. So we have 4 squared, which is, or sorry, 2 squared, which is 4, pi squared, r squared, over t squared, when I work out what this is. And then that equals g m over r. Okay, so we're almost there. Here's what we're going to do next. I'm going to multiply on both sides by r. So now I'll have r cubed here, and then no r right there. I'm going to divide by t squared, because that's already there. And then I'm going to divide through on both sides by 4 pi squared. So on the other side of the equation, I'm going to have gm divided by 4 pi squared. So what is this telling us? This is telling us that the radius cubed divided by the period squared is equal to g m over 4 pi squared. But notice, this whole quantity right here, that's a constant, right? I mean, big G is a constant, 4 and pi, that's all constant, but of course the mass of the sun is also a constant. So this is going to be a constant for any object orbiting the sun. What we've just shown is this quantity, this ratio right here, is going to be constant. It's going to stay the same for any object orbiting the sun. Now, strictly speaking, we've only shown that this is true for a circular orbit, but it can be generalized to elliptical orbits. That's a lot harder to show, but I just want to show you that it works for circular orbits, right? We get that the distance to the third power divided by the period to the second power is constant. It also works for elliptical orbits. Okay, so that's where that's how you can get some sense of where Kepler's third law comes from. Okay, so the next thing we're going to do is use Kepler's third law to make a calculation. So in particular, I want to look at this question. A year on Earth and a year on Mars are not the same thing. If we're defining a year to be how long it takes a planet to go around the sun, well, of course, the Earth takes a certain amount of time to do that, but Mars could take a different amount of time to do that, right? So it's not really the same idea of a year. So it turns out Mars orbits the sun every 697 days. Okay, that's Earth days. And the Earth orbits the sun once every 365 days. That's what a year on Earth means. So we know the distance between the sun and the Earth. That's 93 million miles. Based on this information given, we're going to use Kepler's third law to find the distance of Mars's orbit. So how far is Mars from the sun, in other words? So that's Kepler's third law. Remember, the ratio of t squared divided by semi-major axis cubed is something that stays constant. So what we can do is compare the Earth and Mars in terms of this quantity and solve for what we're looking for. So pause the video, see if you can work this out, and then we'll go through it. Okay, so on to the solution. So the notation here I'm going to use is E, that's the Earth, M, that's Mars. Remember that T is the orbital period, and then S is the semi-major axis of the orbit. Okay? So Kepler's third law says that we can take the ratio of the orbital period of Earth squared divided by the semi-major axis of Earth's orbit cubed, and that should equal the period of Mars's orbit squared divided by the semi-major axis of Mars's orbit cubed. And what we're looking for is the semi-major axis of Mars's orbit, because that's telling us something about how far from the sun Mars is. Okay, so solve for Sm. So Sm cubed is going to be equal to, I'm going to have to multiply on both sides by Sm to put it over here on the left side, on top. Then I'm going to divide out Te squared and multiply Se cubed. So you got that? We have Se cubed on this side now. We're going to have Tm squared over Te squared. As I was saying, Sm cubed is equal to Se cubed, Tm squared over Te squared. Now, the variable I'm trying to solve for is being taken to the third power here. And if I wanted to solve for it, I can take the 1/3 power of that. So if I have something to the third power and then to the 1/3 power, that just gives me the first power, which is Sn. So on the other side, I'm going to have Se cubed Tm over Te. Actually, that's all squared, right? And then I'm taking that to the 1/3 power. So I have to take both sides to the 1/3 power to solve for what I'm looking for. So Sm is equal to, all right, if I take Se to the 3rd power, and then take that to the 1/3 power, I just get Se. If I take something squared, and then take that to the 1/3 power, that's the same as having the 2/3 power. Okay, so it's a fractional power. And then we have Tm over Te. So when you use Kepler's law, you do have to get used to, or Kepler's third law, I should say. You do have to get used to these properties of powers. Okay, we're going to use that stuff. So, okay, so what's Se? Well, that would be 93 million miles. That's the distance that Earth orbits the Sun. So it's 93 times 10 to the 6 miles. And then Tm, what is that? It's the period of Mars's orbit. Well, we were told that that is 697 days. And then we have the period of Earth's orbit, which is 365 days. Cancel out days. And then you actually have to take that to the 2/3 power. Okay, so this is what you type in your calculator. And what comes out is 1.43 10 to the 8 miles. Or we can think of this as 143 10 to the 6 miles. Or we could say 143 million miles. So Mars orbits the Sun at a bigger distance than the Earth by quite a bit. And that's just one example of how we use Kepler's third law. We just solved for Mars's distance from the Sun. Okay. Oh, sorry, wrong thing. So that was the example. Now, I think that's it for Kepler's laws of planetary motion. The only one that we're actually going to really make any calculations with is the third law. So really understand how this example works, because you'll see other things like it. And then the last thing I'd like to say about Kepler's laws is, I did mention that orbits of planets are elliptical, so they don't move in perfect circles, and they're not always the same exact distance away from the Sun. However, for most planets, like the Earth, it's really close to a perfect circle. It's just slightly squished along one side. So in a lot of circumstances, we can approximate the orbits of planets as if they're perfect circles. But if you really want to get it right and get the details right, they're actually ellipses. That's the idea. Okay. So now we're going to move on to what I said earlier was going to be sort of just for fun. This is modern ideas of gravity. So nothing we're going to do here is anything I expect you to really do in a homework problem or in a test problem. I really just want to give you some idea as to what has happened in astronomy in the last couple hundred years, because everything I told you about Kepler's laws is about 400 years old. Everything I told you about the work of Isaac Newton is over 300 years old. So, a lot has happened in the last 300 years. I want to tell you about some of that stuff here, okay? So, Newton's law of universal gravitation that we've been discussing for the entire lecture here is really, really powerful, okay? It's done so much to help our understanding of astronomy, and I just want to highlight some of the successes of the law of universal gravitation. So for one, it really gives the correct description of everything in the solar system, from the motion of the Earth, the Moon, and other objects. It really correctly explains how those things happen. It actually explains the tides, so the fact that the water level can go up and down over the course of a day is what we call the tides, and Newton was actually able to explain that using his theory of gravity. It's basically the fact that the gravity of the moon affects water here on Earth. That explains the tides. Also, if we didn't have Isaac Newton discovering everything he did about gravity, there's no way we would have the knowledge we need to send, let's say, a satellite into space, or to send a person into space, or land on the moon, right? So this is really important work for all kinds of modern applications. And also, it's really worth mentioning that Newton's theory of gravity gave us a way to detect objects that can't be seen directly. Okay, so for instance, we all know that there's a planet in our outer solar system called Neptune. But did you know that the way Neptune was discovered is that the planet that's before Neptune, a little bit closer to the sun, is called Uranus, and this planet had sort of weird things going on with its orbit. It wasn't moving in exactly the way that people predicted, and this was the mid-1800s. Someone made a calculation that the reason Uranus is moving in a weird way that we can't explain is because there's another planet out there that's causing the orbit to change slightly, and in fact that planet is Neptune. Okay, so the whole way the planet Neptune was discovered was based on how it was affecting the orbit of another planet. So with all those successes, there are a lot of problems with Newton's theory of gravity. Okay, and actually, I want to tell you about some of those problems. So, the first thing is something called action at a distance, because the theory implies that, look, if I have two objects separated by some distance, they're exerting forces on each other, but they're not touching each other. That's strange. That's not something we're used to, because up until this point, all forces we've seen, like, let's say, a normal force, the reason there's a normal force between my hands and the table is because I'm pushing down on the table. There's physical contact. And as soon as my hands leave the table, there is no normal force. So every other force like that, friction is another example, it depends on physical contact. But it looks like gravity can just be exerted without any physical contact. That was a problem kind of theoretically. Like, what is happening if there's no physical contact? How are they exerting a force on each other? The other thing is that if you take Newton's theory seriously, it really implies that the effects of gravity are transmitted instantaneously. Okay, so it doesn't matter if I'm talking about these two objects, right? They pull on each other with the force of gravity, and how long does it take for the gravity to get from here to here? Well, according to Newton, it just happens immediately. But what if I weren't talking about two objects that were so close together? Let's talk about, for example, the Milky Way galaxy and the Andromeda galaxy. Okay, they're millions of light years apart. Is it the case that the Andromeda galaxy pulls on the Milky Way galaxy with the force of gravity just instantaneously? It takes no time for the gravity to get from one place to the other? That was sort of a weird idea, and people had a problem with it. Because, think about this. In every other context, when you want to send a signal, okay, from one place to another, it's going to take some amount of time. It's going to move at a finite speed. So for instance, I could send a signal through the air using sound. Okay, well, the speed of sound is like 343 meters per second. I could also send a signal using light, but light doesn't just travel infinitely fast. It travels at 3 times 10 to the 8 meters per second. So in every other context, we expect things to move or be transmitted at a finite speed, but apparently, according to Newton, gravity doesn't work that way. So that's a really big problem with the theory. And so, to kind of sum up what the problem is, let me read you a quote. That one body may act upon another at a distance, through a vacuum, without the mediation of anything else, and by which their action and force may be conveyed from one another, is to me so great an absurdity that I believe no man who has, in philosophic matters, a competent faculty of thinking could ever fall into it. Okay, so, just taking the sort of fancy language out of this, just saying that there's no way you could believe that gravity just moves across the universe from one object to another instantaneously without having to be carried through some kind of medium, like the air, right? And you know who said this? So try to guess. Who do you think said that? Was it, I don't know, Derek Jeter? No, it was actually Isaac Newton himself. So he even knew there was something deeply wrong with his own theory. And he didn't have a big enough ego to say, my theory is absolutely correct, there's nothing wrong with it. No, he knew there was something wrong with his own theory. But he just never was able to figure out the solution. It wasn't until hundreds of years later, when this guy, Albert Einstein, comes on the scene, that he resolved a lot of these issues with Newton's theory. So in 1915, Albert Einstein developed what is now called the theory of general relativity, which explains in a much more deep way how gravity works. Okay? So the basics of the theory is this. Space and time are dynamic. Okay, so you can warp or distort space and time by having massive objects or really high amounts of energy present. Okay? And if space gets distorted, and I have an object moving through that space, well then the path that that object takes is also going to be distorted a little bit. So for instance, if something that would normally move in a straight line is in the presence of the Earth, that path is going to be distorted, and now it's going to be moving in a circular orbit around the Earth. That's really the explanation that Einstein came up with for gravity. So it gives a much deeper explanation as to what's going on. And, you don't really need to know about this equation, but here's what it says. On one side, you have an expression that tells you something about the curvature of space-time. So these distortions that are being shown over here. Okay? On the other side, you have some constants. And then you have something that tells you about how mass and energy are distributed around that space. So this is a really good quote that I like, and it's by John Archibald Wheeler. And he really just summed up what Einstein's theory is all about. Mass tells space-time how to curve. And then space-time tells mass how to move. So again, the idea is, if the Earth is present, it's going to distort space and time around it. And then if there's an object like this satellite, let's say, in the vicinity of the Earth, it's going to move in a different way from before. Its path is going to be altered. Okay, so I want to tell you guys, just real quick, a couple really cool effects in general relativity. One thing that general relativity, or GR, that's what we use for short, predicts is that the light, the path that light takes is going to be bent when it passes by a massive object, and this is called gravitational lensing. So just like if you wear glasses or contacts, the material in your glasses or contacts bends light, apparently so does gravity. Okay, gravity can bend light in a similar way. And this was actually observed for the first time in 1919 by an astronomer named Arthur Eddington. So here was the idea. This observation took place during a solar eclipse, so the moon was blocking out the sun at the time, and there was a star that was known to be behind the sun. So we know it's actually behind the sun. We should not be seeing it because it's just being blocked by the sun. Yet, it was still seen because what was actually happening was the light from the star was bent. It was warped in its path towards the Earth. And so we actually did see it even though we shouldn't have. Okay? So that's gravitational lensing. We can see something that's behind the sun because the path that light takes actually bends around the sun. And that was a really good verification of Einstein's theory. And now this idea of gravitational lensing is pretty commonplace. I mean, there are just countless examples of where you can see this if you just look out in the universe. And these are two images taken by the Hubble Space Telescope. And the first one, what are we seeing here? This looks a little strange. Well, what you're seeing is, in the background, there is a spiral galaxy, something that kind of looks like a disk. And in the foreground, we have a really massive elliptical galaxy. And so the light from the spiral galaxy is being bent on its way to Earth by this really massive object in front of it. So instead of seeing just a normal disk shape, we see this completely warped shape due to this gravitational lensing. Okay? Here's another example over here. And again, there are just countless examples of gravitational lensing you can find taken by the Hubble Space Telescope. Okay. So again, I'm just kind of running through a couple things real quick. Some cool effects of general relativity. The next thing is gravitational time dilation. Okay, so it turns out gravity affects the passage of time. So remember when I said we're talking about the warping or the curving of space and time. This is talking about how gravity affects the passage of time. And the basic idea is clocks move slower. They tick slower for observers in a stronger gravitational field. Okay? And this is actually a well-established fact. Okay, we really know this is true. It's been measured in a lab. So we know that gravity, the strength of Earth's gravity, depends on how close to the surface you are. So if you go higher up, gravity gets weaker and weaker. But let's think about a clock right at ground level, and then another clock just 1 foot above it. So technically, the clock that's a little higher up is in a weaker gravitational field than the one below it. So according to general relativity, the clock on the bottom is going to tick a little bit slower. So time is going to move a little bit slower for the clock on the bottom. And that's actually been measured. With a height difference of just 1 foot, you can measure this gravitational time dilation. Now, I'm sure a lot of you have seen the movie Interstellar, and I guess I should just say spoilers are coming. The effect of time dilation was used as a plot device in the movie Interstellar. So the idea was there was one person hanging out really close to a black hole, and there was another person in a spaceship further away from that black hole. And by the time they met back up, okay, one person thought that 4 hours had gone by. It was like nothing. The other person aged like 20 years. Okay, so this really strong difference in how time passes, it is a real effect, and it's been used in sci-fi movies. Okay. The next cool effect of general relativity that I want to talk about is something called gravitational waves. Okay? So I want you to think about just what a wave is in general. So if I take my hand and put it in a container of water, like a bathtub, and I just sort of move it up and down, what am I doing? I'm creating waves in the surface of the water that move outwards from where my hand is. Similarly, you can have a gravitational wave, which just means that if I have a massive object and it's moving back and forth, like my hand in the water is accelerating in some way, I can send out ripples in space-time that move out at the speed of light. That's a gravitational wave. And it's really important to note that it moves at the speed of light, so it actually doesn't move infinitely fast. It moves at the speed of light. So this is how Einstein kind of solved Newton's problem that we talked about earlier. Now, Einstein himself, because he worked out the theory of general relativity, he knew, just based on making calculations on paper, that gravitational waves should exist. However, that was in 1916. It wasn't until exactly 100 years later that gravitational waves were first detected. Okay? So the first time gravitational waves were ever found was in 2016 by this experiment called LIGO. And what was it that this LIGO experiment detected? Well, they basically detected two black holes crashing into each other, creating massive gravitational waves. So this is sort of a rough sketch, a rough animation of what that looks like. So these two black holes spiraling into each other, sending out gravitational waves. Okay, so I'm going to show you a little bit about the LIGO experiment. LIGO stands for Laser Interferometer Gravitational Wave Observatory. And this is an animation that shows you how it works. Okay, so the first thing is we have a laser which is split into two separate paths. Those two laser beams bounce off mirrors and then they come back and they recombine. So you split the laser in two and then you combine it again. And so the way light combines is kind of interesting. If the two laser beams travel the same distance, it turns out you get a really bright signal, okay, detected when they recombine. However, if the two laser beams travel a different distance, then the signal is going to be less bright. Okay? Now what could cause the two laser beams to travel a different distance? Well, it turns out if a gravitational wave comes in, it distorts the space, causing lengths to get bigger and smaller. And that's where you're going to see that light, which normally would be very bright, going dimmer and dimmer. And that's exactly how they calculated or detected gravitational waves in the LIGO experiment. Now, this is a really, really delicate experiment. Okay, they're trying to measure tiny, tiny little variations in the movement of these mirrors. And so to really make sure what they were seeing was real, they duplicated the experiment. Okay, there's an observatory in Washington and another one in Louisiana. Pretty much they both work this way. And they saw the same signal at the same time. So it wasn't just a fluke, right? If they both saw the same signal at the same time, that's really strong evidence that this was something real and it wasn't just measurement error. Okay, so I think we have time for maybe one practice problem on gravity. And so, how about we do the first one from the lecture? This says, a mysterious newly discovered planet has a radius of 6,500 kilometers and a mass of 4.5 times 10 to the 23 kilograms. So suppose you want to launch a satellite into circular orbit around this planet so that you can observe what's going on the surface. You want to take some pictures, maybe learn something about the planet. So we want the satellite to have an altitude of 250 kilometers above the surface. So the question is, what speed should we launch the satellite? So how fast does it need to be moving in order to orbit in this circular way? So for that, we'll go to the document cam. Okay, so here's what we're dealing with. So big M is going to be the planet. The radius, we're going to call that big R. Now, the satellite, little m, is at an altitude, which we'll call h, above the surface of the planet. Now, what's going to be relevant later on is the distance between the center of the planet and the satellite. So let's call that lowercase r. And then this is going to be the circular orbit, or the path that this satellite moves in. Okay? So the question is, how fast is it moving in that circular orbit? Okay, so first thing is the distance from the center is equal to lowercase r, which is equal to uppercase R plus h. We need to know that value, so let's just calculate it. It's going to be 6,500 kilometers plus 250 kilometers, and that's 6,750 kilometers. Now we can convert that to meters, because 6,050 kilometers is 6,050 times 10 to the 3 meters, or 6.75 10 to the 6 meters. Okay, so again, that's the satellite's distance from the center of the planet. Now that we know that, we're going to use Newton's second law, F equals ma, but in the radial direction. Now the force on this satellite is gravity. It's going inwards towards the center of the planet. It's big G, big M, little m, divided by r squared. And keep in mind, we need to use this distance from the center. That's what is actually relevant here. On the other side of the equation, we have little m, and then v squared divided by r. So if I'm looking for the orbital speed, let's try to isolate v on one side. So cancel out the mass of the satellite, multiply through by r, gives us gm over r equals v squared. So if I want v, I need to square root both sides, which would be the square root of gm over r. And let's put a number to that. So big G is 6.67, 10 to the minus 11, newtons meters squared per kilogram squared. The mass, that would be big M, the mass of the planet, 4.5, 10 to the 23rd power kilograms. And the radius of the orbit is 6.75, 10 to the 6 meters. That's what we need to calculate. So the result of this is 2.11 times 10 to the 3 meters per second, but 10 to the 3 meters is a kilometer. I could just as easily write this as 2.1 kilometers per second, keeping two sig figs. So 2.1 kilometers per second, that's the speed we need. Okay, the next thing is the orbital period. That's the orbital speed. The orbital period is going to be, well, let's think of speed as distance divided by time. The distance you travel in one period is the circumference, 2 pi r. So we go around the circle once. And t is the period. So what I want to do is solve for the period, solve for t. Rearrange this to say t is 2 pi r divided by v. And let's plug in what we know. 2 pi, radius 6.75, 10 to the 6 meters, divide by 2.11, 10 to the 3 meters per second. So what happens, that's our speed in meters per second. Meters cancel out as a unit, and we're left with seconds. So in particular, we have 2.01 times 10 to the 4 seconds. Now, if we convert that to hours, we'll get the unit we want. 2.01 10 to the 4 seconds, multiply, what do we have? 60 seconds in 1 minute, cancel out seconds, and 60 minutes in 1 hour, cancel out minutes. So the orbital period, if you make the calculation, is 5.6 hours. That's how long it takes the satellite to go around the planet one time, 5.6 hours. And that's how it works. So, that's really it for the lecture on gravity. There are a whole bunch of other practice problems that you can do. Again, those are on Canvas, and the answers, you can find those on Canvas as well. So do those for extra practice, and I'll see you in the next one. In the meantime, stay safe, stay healthy out there.